Hello, how are you? I want to continue now talking about the internet layer. This may be the last one on the internet layer. It may be the next to last one. Remember, the internet layer, again, is the third layer we've talked about. It's called the level 3 layer. We had the application layer first. That's level 5. We had the transport layer. That was level 4. And now we're at level 3, the network layer or internet layer. And what we've been looking at is how we use the IP addresses, and we started talking about how we route things across the internet. There were two algorithms we looked at. The link state algorithm is the Dijkstra algorithm. The distance vector algorithm is the Bellman-Ford algorithm. You've had homework on both of them. On Dijkstra, you had to do Dijkstra for a small network. And on distance vector algorithm, you had to write the algorithm and get it working. Now, there's an interesting problem, especially with, say, the Bellman-Ford algorithm. It's called the countdown to infinity problem. To illustrate it, I'm going to take this example here. If you look there, that's a simple network. And we have two paths that A could take to D. But when we do any reasonable algorithm, the path is going to be A to B to D. It's length 3, and the other one is length 14. So we don't want to take the 14. Now, what do? Pardon me, I want to get this all on one page. Still can't do a very good job of getting it there. Let me try one more. Let's see if I can get rid of this. And I'm going to bring it down just a little in size. Sorry, but I do want to see if I can get it on one page. All right. So, there's our network, and now I'm going to have something happen. What I'm going to have happen is that the connection between B and D dies. So we begin with the connection dying. This could happen. Now that means that B has no way to D. So B says, all right, I will ask my neighbors how to get to D. And B sends a request to A, how to get to D. Now A has a path to D. A's path to D takes 3. By looking at the network, we know that path goes through B, but that's not what A is going to say. A is going to say, I have a path that takes me 3. Well, B is going to say, I take 2 to you, and you take 3 to D. Well, that means that I have a path to D of length 5. Now, B sends its updated table to A. A recomputes its path. It's now saying, well, I go 2 to B, and B has a 5 path to D. So that makes my path 7. So I now have a path of 7. And of course, I send that over to B. Well, B recomputes its path to D. 2 to A plus 7. B now says I have a path of 9. B sends its updated table to A. A recomputes and gets to, pardon me, it was, I made a mistake there. It was plus 9. So this should have been 11. Apparently, And this should have been 13. And now the 13 comes out to 15. And now BA advertises a 14 path to D. A, since it's updated table, it computes the path of 2 plus 14. That gives it 16. B, since it's updated table, the path through C is better than through B, and no change in A's table. So we have finally settled down. Now it took a while because the second best path was unfortunately much bigger. As I said, this is called the countdown to infinity. It's also known as bad news travels slowly. You could prevent this some of the time by having what's called a poisoned reverse. In other words, when I send A my table, I don't advertise any tables that go through B. I may pick the second best table, but I simply, well, no, I don't even that. I just don't advertise any paths that go through B. So B has to figure out from other neighbors how it can get to D. Because if A were to, it'd go right through B. This doesn't solve the problem entirely, though. It is possible that the path uses some other router further down, and we could that has broken, and we really can't get rid of it. Now, both Dykstra and Bellman Ford just don't work really nicely when you really up the size of the network. If you did the algorithm, you noticed that there's an awful lot of exchanging going on. Also, in the real world, we can't just say that all nodes are the same. An example I saw on the internet is the following. Suppose you are a backbone company, you're one of the big ones, and you have a West Coast and East Coast portions. And you have another company that has a West Coast and an East Coast portion. Now, Company A wants to send something to the East Coast that is in your network. So it wants to put that information into your network on the West Coast and let you carry it across the internet to the East Coast. However, you wanted to put it into its own West Coast connection and send it on its network to the East Coast, and then have its East Coast network node connect to your East Coast node. both of you want the other network to carry most of the work. So those nodes aren't the same. There are other ideas other than shortest path. It may be who owns that path, who has to pay for it, who's going to be inundated by lots of messages from other systems. And there's a payment problem here. You probably have to pay by how much network, how much you send across the other system, possibly by how far. So we can't just use the two algorithms. There are other things to think about when algorithms are being used. Nonetheless, let's talk about some of the real algorithms that are on the internet. Now, first of all, the internet is far, 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 far too large to run one Dijkstra algorithm or one Bellman-Ford algorithm. So instead, we talk about autonomous systems. So an autonomous system, an AS, may be all the nodes in one ISP group. In other words, one company owns them. Or at least one company, they all are in the same internet service provider group. The ISP could have broken its nodes into several ASs. The point is that an AS is within one, let's use owner in a sense. It's one company can work with it, I guess is to say the way to do it. Now, in that case, what are we trying to find out? We want to know how I can get from any router within my network, my autonomous system, to the router that will send it out to the rest of the world. So this should say external. So each system, say each LAN, like PC's LAN, has a connection to the rest of the world. And each of our nodes inside has to figure out how to get there. So one algorithm works inside an AS. It's called the internal gateway protocols, or I think they may have a fancier name, maybe IBGP. The best known ones are RIP and Open System Path First, I think it's called. Shortest path first, pardon me, which is very much like a Dijkstra. Cisco does not tell us how it does it. The O stands for open, and Cisco's is not open to the rest of us to see. Now, RIP is distance vector. It's more like Bellman-Ford than like Dijkstra. The OSP is more like Dijkstra. There are two versions. Version 2 is more modern. Version 1 was meant to work with IPv4. It came out with Unix in 1982. It has a very simple metric, the number of hops. So how many routers you're going to go through. And it basically says If we're getting above 16 hops, we're at infinity. That's too many. There should be no path. That's the shortest path is that long. Every 30 seconds, the nodes exchange their routing tables. They send out information on 25 nets. And if no advertisement after 180 seconds, RIP decides the link is down. The routes through that neighbor are not there anymore. And the neighbors in turn send new advertisements if their tables have changed, as I did with the countdown to infinity. Notification of the link failure goes to every node because of the exchanging of tables. And it uses the poison reverse we talked about. So that's one algorithm that's really in use. The OS path first is Dijkstra. What it does is it sends advertisements of its route using flooding. Flooding means it sends it to every one of its neighbors. Now you got to be careful on flooding. If I send it to a neighbor and that neighbor has a neighbor in common with me, then the common neighbor is going to get 2 copies of it. So the method that's used to keep called tamping down the flooding, I think would be the way to put it, is to say, we're going to put a number in the message we send out. Every time a node receives it, it should subtract 1 from that message. If that number is 0, it means it should have received it already. Don't send it on. It's got to be a duplicate. So we say how, we could say like, if this has gone through 16 nodes to get to you, you receive that information probably from some other path. Don't bother flooding it out to all the network. That is one way to prevent things from duplicating all over the place. There are other methods called spanning trees. Also, if you've already received it, don't send it. So you use TCP, not UDP, to send the messages. Now, IS-IS algorithms. These connect the intermediate systems used in the path. We'll talk about those later. OSPF can also be looked at as the example of a finite state machine. The router is in 8 states, and it goes around these states. You can see the states there. I'm not going to go through them all, but it's another example of an automata, a finite state machine. As I said, there are many, many, many of them in computer science. Now, I'm going to have some more information on those in a while, but I'd also like to talk about the Internet Control Message Protocol. This is used by routers and network devices to send error messages and indicate success or failure. I can show you some of this. I did a Wireshark capture yesterday, and I'll go down to get, first I have to order them by that, and now I'll try to get down to the ARP is Address Resolution Protocol, and as you can see, it comes up a lot. Here we are. These are the ICMPs. And there's the version 6 and the version 4 ones. The version ones here, if you look at them, they're involved with pinging. That's what they're all about. I did a ping of several places to see how it would work. And it's the one at the very top here. I pinged 163.1.221.216. The system pinged it 4 times. Excuse me. And then took the average of them. I know it did that because I saved the command line pinging so I could make sure that I was seeing what was going to happen. Here it is. This was my pinging. And you could see I had the 4 pings, the bytes, the time to live. So pinging uses ICMP. ICMP is a strange algorithm in one sense. There's something missing. If you look in here, look at this algorithm. Look at what I have here. Oh, pardon me. And I lost that, so let's go back. And I got to go back here. And I got to get back down there. Now, if you look here, let's take an ICMP item here. We'll take the first one. If you look, there's something missing. There's no transport protocol. ICMP puts itself sort of piggyback on the IP. That's how it gets around. And it has a set of types. Type 8 is an echo ping request. And the response is in 924, which I just brought up there. And it tells you it's a type 0 echo ping reply. So ping uses that. Now there's also another use of the ICMP that's easy to see. This is the trace search. I got to find the one I did. It's hard to see these, but these are all pings. Let's click on one of these. We use the ping, but the return is a little bit, when we get it back, pardon me, when we send out a trace the route, what we do is we give it a time to live of 1, which means it only can go 1 node. So when it gets to that 1 node, that node will inform us that it couldn't pass it on because its time limit exceeded. We don't care because all we wanted to know was what was the IP of that first node. Didn't bother us. Then, we'd like to know the second node. So we send out one with a time to live of 2. And now the second node sends us back information. So we know the IP of the second node. And we keep doing that and doing that and doing that. It's not guaranteed that we're going to get the same path each time we send out of one of these requests, because unfortunately it may take a different route, at a different time. But at least we will see some way to get there, piece by piece. So those are ICMPs. I am putting together a homework with Wireshark involving ICMPs. ICMP is kind of complicated. I've looked at it. There are some things we can't find out with Wireshark. They just don't travel along the proper Ethernet command lines, and Wireshark doesn't catch them. I looked to see if there was any way to catch them, and there may be some kludgy approaches to it, but I didn't think it was worth pursuing. ICMP is another one of the algorithms at this level, at the IP level. So we've seen two algorithms at the IP level, ICMP and IP. There is also one called IP Security Protocol, and it's used in the virtual private networks. In other words, you set up your own network. Don't want anybody else really using it for security. Now, let's get back to looking at algorithms. Every one of the routers we can think of as a gateway. The routers that connect to ASs, a router connecting to different ASs is a border gateway. It gets us from one to another. A router within an AS is an interior gateway. And that's kind of an important concept to the way routing goes. I won't go through all those. The text has a pretty good examples of those. And in the next and last of my material on the internet, I'll talk about those. So good luck now. See you later.